Our next speaker is Dr. Jeremy Levitt from Mentor, a Siemens business. He's a principal engineer in the formal verification team. Dr. Levitt is in the formal verification group of Mentor. He oversees R&D with a focus on algorithm development. Jeremy earned his PhD in electrical engineering from Stanford in 1997, an MS in 1993, and the BASc in engineering science from the University of Toronto in 1991. And the title of his presentation this morning is Exhaustively Verify SEU Mitigation Techniques Using Formal Verification.
Okay, thank you for the introduction, and good morning, everyone. It's still morning. I'm going to talk about using formal verification to verify logic added to your design to make it fault tolerant, to guard against single event upsets, stuckats, this sort of thing, and verifying this using formal verification. So here's a outline of the talk. I'll first of all have an introduction, and then I'll jump into the current way this sort of logic is verified using simulation and the challenges with using simulation. And then I'll present using formal verification in an automated manner to perform the verification. And finally, I'll wrap up with industrial application of this technique. All right, so this talk is going to focus, when you talk about making designs fault tolerant, there are many aspects you could take. You could change the hardware, change the technology to make faults less likely. You could address it in software. This talk focuses on actual hardware added at the RTL level to both detect and warn about faults or to detect and correct faults. And so some examples of what's called these safety mechanisms are tri-mode redundancy, TMR logic, error correcting codes for checking issues with data paths. You can encode your FSMs using one-hot, so that if there's a bit flip somewhere, you can recognize it. And there are various techniques you can do to harden your design against faults. The faults we're talking about, which is a pretty general category, it's single event upset, which might be due to radiation in space environments. As the hardware fails, you might have a stuck at 1, stuck at 0 problem, transient errors, etc. So once you've added this mitigation logic to your design, how do you verify that what you added it both correctly and that it actually mitigates all the issues you want mitigated? And historically, of course, the way to verify everything is through simulation. And this is a formal community here, so we will understand that the problem with simulation is it's only as good as the test you wrote. And it's quite hard to write good test benches and get high quality simulation. And trying to do this to verify the robustness of your design in the presence of faults is even more challenging. So what became one test now has to be replicated for every single fault you want to test against. And on top of that, you have this overhead of making sure that you actually added the safety mechanisms to the critical logic you want to protect against faults. So this is both logistically difficult to collect all information and track it all. And writing the tests is also manually a fair amount of effort and takes time. So the bottom line is that single event upsets, faults in general, you can't verify exhaustively, of course, with simulation, but more than that, it takes a lot of effort, both in terms of compute resources and manual time to do this. So can we do better? So, of course, another approach is to apply formal verification to this task. And the picture here shows you what we're going to try to do. We're going to try to take our design with the, in this example we have TMR, but whatever safety mechanisms you added to it to make it more robust. And we're going to compare it with that same design, but we're going to modify it slightly to take a node and allow formal to inject a fault, to flip the bit or flip the signal at a time of its choosing. And now if in this case, the TMR logic is working correctly, flipping one bit shouldn't have any output, shouldn't have any impact on the results, because the TMR logic will detect that there's a problem and correct it before it gets out. And so we can pose this as a formal problem and then mathematically prove, of course, that no matter what happens, this fault will be corrected. I could probably skip this slide, except the last bullet here. The point is that you're letting Formal choose when to inject this fault. So essentially, Formal is going to be considering all possible injections under all possible scenarios, which of course is not something you can do in simulation. So rather than the person running the simulation try to figure out when should I inject this fault and under what situation to get it to propagate to the output without being detected, you're letting Formal do all this work. Now it turns out that there is a very useful app, Slack, for verifying two different designs or two different versions of the design and determining whether or not they have the same functionality, the same output behavior. And traditionally, these sorts of Slack tools are used to verify ECOs or maybe clock gating logic which has been added. But we can use it, we have now these two different versions of design, we can use it to verify that our design with the fault and the design without the fault behave the same way. And again, this is completely formal, so it's exhaustive, gives us a level of verification we can't hope to get with simulation. So taking the Slack flow, what we do is for design A, we take our DUT with the safety mechanisms we added, the TMR, the one-hot encoding, whatever techniques we used. And as our design B, we take that same design with the modification that allows Formal to inject the fault whenever it wants. And you'll see above the beige box here, we have fault generation and reduction. So there are a lot of faults we want to test, and there's some easy pruning we can do to reduce the number of faults we need to worry about before we actually start running them through this somewhat expensive Formal tool, expensive in terms of time. And then the output of the Slack tool will tell us either that the output behavior is the same, no matter what Formal, no matter how Formal tries to inject this particular fault, which tells us that that fault is safe. The safe mechanism either detects and warns, or it detects and corrects, and there's no way that fault can propagate from that point. Or it will give us a counterexample, showing us an exact scenario where the fault was injected, and then the logic was sensitized to propagate it all the way to an output without triggering any detection logic. Okay, so let me talk about this reduction phase, or fault pruning. And this is actually very, very simple, which also means it's a very fast approach. The first observation here is that we're only interested in faults which propagate to the outputs. And so any logic which is not in the cone of influence of an output we care about, we don't care about faults on that logic. So obviously faults on logic which isn't connected to the output can't affect our outputs. So we can immediately prune out any faults on those logic. And then the next step, taking this a little bit further, is to consider the fact that usually we're interested only in making I shouldn't say only, usually our main focus is on making the device robust in its normal operating mode. So what we can do is we can disable the test logic, we can disable the DFT logic, disable scan chains. We can remove from consideration any logic which is not part of normal operating mode, and that can further reduce faults. We don't need to worry about faults in that part of the logic. So all this can be done upfront and very cheaply and efficiently. And now we can take this a step further and consider what happens with the detection logic we added. Obviously, we can only detect issues, or we can only detect faults which are actually in the cone of influence of the detection logic. So we can run a very quick pass of the design and partition the logic into logic which is potentially detected because it's in the fan end of some detection logic, or logic which is in the fan end of an output we care about and not in the fan end of any detection logic. And this is useful. So those sorts of the logic which is not in the cone of influence of the detection logic, but in the cone of influence of a fan out we care about, that is a potential detectable fault. All that has to happen is that needs to be propagated to the output and you have a problem. So this is useful because right up front, without doing any coverage or running any analysis, we can quickly get a idea of where we need to put our safety mechanisms. So this is very helpful to get a quick view of where the safety mechanisms need to go in so we can get the critical parts of the design covered. So once we've figured out where we want to put our safety mechanisms, we've added this logic to our design, then we can run it through the Slack flow and check each individual fault injection point and see if our design is now robust against these sorts of faults. The tool will give us, for each fault, will give us one of two outputs. Actually, there's a third output which is inconclusive, but we'll not dwell on that. The first result is it could tell you this fault is safe. So there is no possible stimulus which propagates this fault to the output undetected. And then the second result is that it does find a stimulus, which the fault's injected, and it's able to propagate, it's able to sensitize the path all the way to an output while avoiding the detection logic. And so in that case, you get a counterexample, which looks like this. And here, for every signal in the design, you have two values. You have the value of the original design without the fault injection, and you have the version of the value for the modified design with the fault injection. And at the point where the fault's injected, you're going to have a difference on that signal. And that difference, in this case, is going to propagate throughout the design and to an output. And so when you bring up the waveforms, you can quickly see the red sections, and follow the difference that propagates through your design without triggering any detection logic. And then based on this counterexample, you can figure out, what's wrong. Is my safety mechanisms, are they hooked up incorrectly? Am I missing some safety mechanisms you can subsequently debug? Okay, this is all great, but of course, you might have thousands of faults. So you also need an easy way to manage and view the progress of your verification. And so for this, the results of the formal analysis are written out into the coverage database, and the test plan is also generated. And then you can bring up the test plan on the coverage database, and you can quickly visualize the status of your verification and compute your verification metrics. So this is an important step in automating the flow and making it usable for people who aren't formal experts. All right, so let me move on to the application of this on an industrial design. So we worked with an auto system supplier, and in particular, they were designing logic for an anti-lock brake system. So this is exactly the sort of thing which you really want to be correctly implemented and robust in the presence of faults. This equipment is going to be on the road for decades, so you not only have random faults which could happen, but the hardware eventually will wear out, and you want it to wear out and in a robust sort of way and not catastrophically fail on you. So we were working with a small team, and they were new to formal. So especially in this sort of situation, an automated approach was essential, because not being formal experts is a little bit overwhelming if you want to combine this sort of verification methodology with having to learn formal. So based on their needs, the application engineers worked with the customer and put together scripts on top of the Quest to Select app so that they could very easily specify what sort of faults they wanted to model, and then generate the test plans, generate the tool setup. Then they could run the tool and bring up the test plan results and see how they were doing. And this effort started about 2 years ago. And the results initially we have here, they had 2,000 fault points, or critical registers in their design. It's not a large design. And in less than an hour of runtime, using this approach, we were able to prove that 90% of those faults were safe. The safety mechanisms they had in place would prevent those faults from ever propagating to an output undetected. And the other 10% were able to show, those were unsafe. We could produce stimulus showing that under these scenarios, a fault here could propagate to your output and be undetected. And at that point, it's up to the user or customer to determine if the diagnostic coverage there is high enough. 10% might be acceptable, or if it's not, then they have the counterexamples to go and figure out where they need to add additional logic. So based on those results, of course, the customer was very happy and is working to apply this approach to other designs. And as I said, this is work which is almost 2 years old. These results were presented at DVCon Europe last year, if you want to read more about it. Okay, so in summary, the need to build robust robust, fault-tolerant systems is increasing. It's long been a requirement in the mil-aero for DO-254 and other requirements, but now increasingly in the automotive industry with ISO 26262 is being a requirement that fault tolerance be built into automotive electronics. So this is both sort of an ethical and legally mandatory requirement. Simulation-based approaches are not exhaustive. So formal obviously has that advantage over them, but they also take a fair amount of time and effort to deploy. On the other hand, applying formal verification to this problem is exhaustive. It tells you exactly which faults are safe and which faults will propagate and gives you the counterexamples so you can debug it. And this increases the quality of your device and reduces the risk of having a catastrophic failure. Okay.
Thank you very much. So we do have time for questions. If any questions from the audience?
Hi, Will Keane from Arm. Just a question on you had a diagram, I think slide 8, on the initial SEC setup. So you've got the DUT plus safety mechanism against the one with the fault generation and the safety mechanism. Could you also not add an additional step of DUT without the safety mechanism?
Actually, yes, I forgot to mention that. Yeah. Thank you. So that's another very excellent use of this. When you add the safety mechanisms, in the process of doing that, you can actually break the functionality of your original device. So you definitely want to do this step of verifying your original device against the device with a safety mechanism.
I was also going to suggest that you can determine which faults are actually faults that propagate when you don't have a safety mechanism to protect you from them propagating. So it could be that you're proving with your methodology that a bunch of completely safe faults, i.e. faults that are handled even without the safety mechanism, they never propagate, but that doesn't tell us anything. So you could use an additional filter step of filtering them out.
Right, so you're saying you could add safety mechanisms which are redundant, don't actually accomplish anything. Yeah, that's a good point.
Consultancy fee will be in the post, I presume more. We do have one question online. Do you hierarchically go to the fault injection circuit and inject the faults?
Let me think. Actually, what we do is we introduce a cut point. So for formal, you can define a cut point, and we introduce a cut point, and there's the driver is and it's a conditional cut point. So basically, the logic is modified hierarchically, but it's done through directives to the tools.
Okay.
So the scripts will script this up, and it all happens automatically.
Okay. I think also they're saying, can you do it from the top level and then automatically find those safety mechanisms, or do you do it all at block level as well as the follow-up question? Right?
So with this, in the designs we've been working with are for ABS, this sort of stuff, they tend to be fairly small. It's not like a big SoC. So these are run from the top level, but it's ridiculously small top level compared to the sorts of chips other people might be working on.
Okay. And have you done any larger designs?
What's that?
Have you worked on any larger designs or not?
No, the safety critical stuff we've been working on has tended to be, not SoC type designs, but more embedded hardware.
And one other question: is the tool qualified for the various standards, such as?
Yeah. So actually, Mentor has or Siemens, I guess now, has a what they call a safe qualification process. So all the tools are being qualified for ISO 26262, and that's an ongoing process.
And DO-254?
I'm not sure there's an explicit qualification for that.
Okay.
The way there is for 26262.
Okay.
Yeah.
Okay. Okay. And they say,
yeah.
Oh, sorry. We have time for, we've got two more questions. We've got time for them both. So.
Yeah, Mohammadi from ARM. So, because this checks for sequential equivalence, do you also factor in interface constraints so that you can?
Yeah, so that actually, that's a good point.
Counterexample will have only valid stimulus, not a.
Yeah, so it depends. The initial approach is ignore the interface constraints, and see if it works. Now you might get some counterexamples due to bogus states or bogus stimulus, in which case users would need to add constraints. And so far they've been using AMBA style protocols, so they can just plug the library in there and get the constraints they need fairly seamlessly.
Sorry. So we can extend this to add more constraints, assertions, or assumptions, and constrain the stimulus, right?
So yeah, I mean the tool
VIPs.
certainly, the flow certainly supports that. It's just that adding constraints is, a nuisance for the user. So you don't want to add them unless they're actually needed.
Okay.
Yeah.
Thank you. Got one last question, please.
Dominic Murphy, ARM. You mentioned when answering the other question, cut points. I assume that's working with you assert the behavior up until the cut point is the same between your two designs, and then you assume it's the same onwards.
Well, actually, what you'd have is you put in a conditional cut point. And the condition is a signal which formal can assert whenever it wants. And when it asserts that signal, it gets the faults injected. When it doesn't assert that signal, it's just connected as normal to whatever logic should be driving it. So essentially, it's just you're putting a mux in there, and whenever formal wants to, or depending on the type of fault, maybe it can only do it once. But it's, formal gets to choose when it can inject the fault, and the rest of the time, the node will function normally.
So that's the method that you use for your injecting the faults into your designs.
That's right. That's right.
Okay.
Yeah.
Okay, I think we've run out of questions in the audience and online, so thank you very much. Thank you.